Welcome to The Explainer. You know, sometimes a simple math problem isn't just a math problem. Today, we're going to look at one where a single calculation could be the difference between an incredible adventure and a really, really bad day. We're talking about a life literally being on the line.
So how do you solve an equation that just can't be solved? I know, it sounds like a riddle, right? But believe it or not, this is a challenge engineers run into all the time. We're going to dig into how they tackle these problems that seem completely impossible on paper and somehow find these really clever practical ways to solve them.
All right, here's our challenge. Imagine this. You and I, we work for a bungee jumping company. The boss comes to us with a super critical safety task. See, medical studies have shown that if a jumper goes faster than 36 meters per second after just 4 seconds of free fall, the risk of injury goes way, way up. So our job? Figure out the absolute maximum safe mass a jumper can have to make sure they stay under that speed limit.
Okay, so to figure this out, we've got to turn to the laws of physics, right? There's a specific equation out there that describes exactly how a jumper's velocity, their mass, and the time they've been falling are all connected.
And here's where we hit a bit of a brick wall. See this equation? It models the jumper's velocity perfectly, but there's a huge catch. That little m for mass, it's all tangled up in there. It's in two different spots, both inside and outside this tanh function. And because of that, you just can't use regular old algebra to get m all by itself on one side of the equal sign. It's impossible. This is what we call an implicit equation, and it's exactly why we can't solve it the normal way.
So what do? Well, here's the really clever part. When you can't solve a problem head-on, you change the problem. Instead of trying to isolate m, we're going to rearrange the whole thing. We'll just move our target velocity over to the other side. So now, our goal isn't what does m equal anymore. Our new goal is to find the one value of m that makes this entire function equal to 0.
And that little shift in thinking, it's actually incredibly powerful. The key insight here is that we've stopped doing algebra and we've started doing something more like analysis. We've just transformed our unsolvable problem into a totally solvable one. And this opens the door to a really fundamental idea in all of engineering.
And this gives our goal a new name. See, a value that makes a function equal to 0 is called a root. So we're not solving for mass anymore. We are now finding the root of our function. And that one special value of mass that makes the whole thing 0, that is the answer to our bungee jumper problem.
Okay, so how do we actually start this search for 0? Well, maybe the most intuitive way is to, stop staring at the numbers for a minute and just look at the picture.
This is what's called the graphical method. It's pretty straightforward. We're just going to plot our function. On the bottom axis, you've got the mass, and on the side axis, you've got the result of our function. And all we have to do is look for the spot where our line crosses that horizontal axis. Why? Because that crossing point is exactly where our function's value is 0. That spot, that's the root we're hunting for.
And when we actually plot our bungee jumper equation, boom, here's what we get. You can see the line dips down, and it crosses that 0 axis somewhere between 140 and 150 kilograms. So just by eyeballing it, our first rough guess for the maximum safe mass is about 145 kilograms. That's around 320 pounds, by the way.
Now let me ask you, is a rough estimate really good enough when someone's safety is on the line? No way, right? Absolutely not. So this graphical method is great. It's fantastic for getting us in the right ballpark, for seeing how the function behaves, but it's not precise. Its real value is giving us a really smart starting point for the more powerful computer methods.
So let's talk about those. Let's see how this visual estimate helps us use the automated methods that engineers actually use in the real world. Once they have that initial ballpark guess, they can turn to two main families of algorithms that will systematically and precisely zero in on the exact answer.
Okay, so these two families are called bracketing methods and open methods. And a good way to think about it is like this. You're choosing between the slow and steady approach that's guaranteed to win the race versus the fast but risky one that might just get you there quicker.
So bracketing methods, they're the sure bet. You give the computer two starting guesses, one on each side of the root, and the algorithm is guaranteed to slowly but surely narrow down the gap and find it. Then you have open methods. These are your high-risk, high-reward choice. They are often way faster, but because they don't have that safety net of a bracket, there's a chance they can kind of get lost and never actually find the solution.
And this whole idea really shows that finding roots isn't just some clever little trick for a bungee jumper problem, It's actually a fundamental way of thinking, a core approach to solving design problems in all sorts of engineering fields.
Think about it. Pretty much any time an engineer needs to figure out a system's properties to get a specific result, they're probably looking for a root. I mean, whether you're balancing the forces to design a bridge, or you're managing the temperature properties of a new material, or you're calculating the right voltage for an electrical circuit, you are very often dealing with one of these messy implicit equations. And that means you're on the hunt for a root.
So let's bring it back. For our bungee jumper, just by reframing the problem, by changing it from solve for m to find the root, we took what was an impossible algebra problem and turned it into a totally solvable one. And it just goes to show you, sometimes the most difficult problems don't need a more complicated solution. They just need a totally different way of looking at them. So what problems out there in your world are just waiting for that little change in perspective?